In this video, I want to derive the Poisson distribution starting from a few basic assumptions and therefore in an intuitive manner. So we start by considering an interval of time. So this is just an interval that goes from 0 to capital T. Let's say we have one axis. In general, you can think of this as an interval of space as well. So you can go from 0 to some length L. It's the same, but I'm going to think of this in terms of time. So we have an interval of time, and we also have another parameter, lambda, that represents the average number of events, quote-unquote events, per unit time. The events can be several things. For example, you can think of these events as particles that are detected. So lambda, in that case, would be the average number of particles that are detected per unit time. And for example, lambda multiplied by t will give you the average number of particles that are detected in this time interval of length capital T. Now we are going to subdivide this interval into smaller chunks with equal length. So this length here of this chunk is delta t. We assume that we have capital N of these chunks. Therefore, capital T is equal to capital N times delta t. Simple as that. And we assume that delta t goes to 0, so it's very small, and capital N therefore must go to infinity, right? If we want to if we want to have a finite time capital T. Now, if we want to, for example, calculate the average number of events or particles or whatever you can think of inside this very small chunk here, well, we know that is equal to lambda multiplied by delta t. And since delta t is very small, we know that this is also a very small quantity, much smaller than 1. And we can interpret this as the probability that only one event occurs in this small interval, this interval here. So this interval is so small that we assume that only one event can occur. So for example, we can think of a particle. In a very small amount of time, we can detect only one particle. That's the assumption. And you can also consider space, as I said earlier. So if you want to think of this in space, you can say, so you can assume, and the assumption in that case would be the following. So in a very small length, in a very small, let's say, space, you would be able to detect only one particle. So this is the assumption. And therefore, here I want to calculate the following interesting probability. The probability that there are k events or k particles inside this interval. This is what I want to find. And we will see that this will coincide with the Poisson distribution. In particular, now let's assume that we want to calculate the probability that we have a particle here. In that case, we know that we have lambda multiplied by delta t. But if we want k particles, then we also have to multiply this probability by the probability that there is one particle here, for example, one particle here, one particle here, and k of such particles. So we have lambda delta t raised to the power k. And in principle, there are several ways in which you can choose the intervals where you detect the particle. So you have several possibilities. And in particular, these possibilities are n choose k. So this is the binomial coefficient n choose k. And of course, in the other n minus k intervals, there must be no particle. So you have 1 minus lambda delta t. So this is the probability that there is no particle inside one of these intervals. And of course, you have n minus k of such intervals. So this is the probability here. Let me repeat it one more time. This is the probability that there are k events in this interval here. Now, you have to remember that delta t is very small and n is very large. So we have to calculate this quantity in such a way that it makes sense. Because in this case, it does not make much of a sense because delta t is very small, it goes to 0, and n is very large. So this is actually a limit that we have to calculate. Now we can rewrite this binomial coefficient by using its definition. This is just n factorial divided by n minus k factorial, k factorial. And then we can rewrite lambda delta t as lambda capital T divided by n raised to the power k. And then we have 1 minus lambda capital T divided by n to the power n minus k. Now, since n is a very large number, we can use the so-called Stirling's approximation that gives us an approximation of the factorial, for the factorial. And in particular, I want to use the following approximation. So n factorial, when n is very large, is approximately n to the power n e to the minus n. And we can use a similar approximation for n minus k factorial. So k can be actually every number from 0 to infinity, but we are assuming that n is so large that this factorial is still very, very large because n goes to infinity. So we have n minus k factorial that we approximate like this: n minus k to the power n minus k e to the minus n minus k. And since n is much larger than k, we can also rewrite this as approximately n. So we can write this as approximately n to the power n minus k e to the minus n minus k. So this is an informal way of deriving this expression, because you can be more formal and you can take into account more terms, but this is what we are going to consider in the approximation. So you have to replace these expressions here. So n factorial, as I said, is just n to the power n e to the minus n, and then we divide by n to the power n minus k e to the minus n minus k, and then we still have k factorial here in the denominator. Let me rewrite it properly. K factorial here, and then we have lambda t over n, lambda t over n to the power k, that actually we can also write it like this. Let me write it like this. We have lambda t to the power k n to the power minus k. So let me write it like this. And then you have 1 minus lambda t over n. And then here I'm going to replace this n minus k with n, because at the end of the day n minus k is very close to n, because n is much larger than k. So in the approximation I'm going to write this. Now you can see here on the left part, you can see that n to the power n times n to the minus k will give me n to the n minus k, which will simplify with this. So this and this will simplify with this. Then in here you can see that since n is much larger than k, we can also rewrite this exponential as e to the minus n, and therefore this will simplify with this, and you will get something which is very close to 1. And when you let capital N go to infinity here, you should realize that this will converge to e to the minus lambda t. So this is the exponential, e to the minus lambda t. And of course, what we get at the end of the day is lambda t to the power k divided by k factorial multiplied by e to the minus lambda t, which is indeed the so-called Poisson distribution. So this is actually a probability that there are k events. And for example, the probability that there is any kind of event, any number of event in our interval would be the sum over all the possible k's from 0 to infinity of this. So lambda t to the power k over k factorial, and then here you have e to the minus lambda t. But of course, you can realize that this is just e to the lambda t. So you have e to the lambda t times e to the minus lambda t, which will give you 1. So, and this makes sense because this is the probability that there is any number of events in our interval. And of course, the probability is 100%. So we get 1 because if we take into account the fact that we might have 0 events, 1 event, 2 events, 3 events, and so on, well, of course, the probability that this happens is 100%. Because if we have many events or just 0 events, this will happen with 100% certainty.